Hey everybody, welcome back to another revised video. Today we have the IB Chemistry Higher Level Paper 1A from the May 2025 examination, Time Zone 1. As always, we're going to go through this paper blind, just try to figure out how to solve each of these questions and explain to you how we got to the answers one by one. And let's get right into it. So question 1, the diagram shows the behavior of protons, neutrons, and electrons in an electric field, and we have a beam of particles shot between a positive and negative electrode, and we're seeing how they diverge in path. Well, how can we answer this? Well, we can easily get make it a 50-50 chance by eliminating these two. The way we do that is we can look at y, and y is a straight path, right? It's not diverging from its path at all from the beam of particles, and this means that we know that it has a neutral charge. And which of these subatomic particles we know is neutral? Neutrons. So we know that y is going to be a neutron. So it's one of these two. Now, as for z and x, well, we can see that x is moving towards the positive electrode, and this means it's likely negative. And for z, it is moving towards the negative electrode, meaning it has a positive charge. Now, the positively charged subatomic particle we know is a proton, and negative is an electron. So that means that our answer would be C. There we go. Question 2. Which of the following species have the same number of electrons? The letters do not represent symbols of elements. Okay, nice. So here the atomic number is going to be useful, so we can look at them. The atomic number for W, we have 12, 16, 21, and 9. Okay, so W, it has 12, it has atomic number of 12, and we know that if it was neutral, it would have 12 electrons correspondingly, but we know it has a charge of 2+, so that means that it has 10 electrons, right? It has 10 electrons. Now, 10 electrons, if we configure it, it would look something like helium, 2p6, right? So this is the outer shell. I just wrote it like in this notation so you can see that this is the outer shell. And if we count the electrons here, that would be 8 electrons, okay? Now let's do it for element X. So X, it has 16, and it gains an electron because it has a negative charge. So that means that we have 17, okay? 17 in the convention, it would be, I believe, neon, 3s2, and 3p5, okay? So that if we add 2 plus 5, that's 7. If you're not following along, just keep a periodic table next to you. I'm referring to one, a periodic table. It's very helpful in this circumstance, but you'll have one during the examination. I just want to pull it up on this screen because it makes it more difficult to switch between tabs. So Y, we have 21, but then we have a loss of 2 electrons, so that gives us 19, okay? So if we were then configuration, we have argon, 3d1, okay? And yeah, in this notation, it means that if we have 3d, we have 3s1, we have the 3s2, 3p6, 3d1, right? So that's the outer shell, so the outer shell has 9. So we have 8, 7, and 9. And then we have Z, which has 9, and then it gains an electron, so we have 10 electrons. And then in notation, that's helium, that's helium, 2s2, 2p6, and that gives us outer shell of 8. So our W and Z have the same, which is D. Yeah, W and Z the same, that's D. Yeah, that's our answer. 3. Which chart shows the neutralization curve of a strong base with a strong acid? This is just acid-base theory. So it's a neutralization of a strong base with a strong acid, so we know that it's not going to be either of these two because neither of these start with a basic pH, right? We want to be, if it's neutralization of a strong base, the initial pH is going to be that of a strong base, which C and B, these ones have initial strong base. Now, if you know that if we're adding a strong acid, we know that the neutralization of it should lead to the pH of a strong acid, which this one does not lead to a pH of a strong acid. Here we see a pH of a strong acid like around 1 to 2 or less than 1. So it's C, right? We don't even need to remember our laws how the curve shape actually is. We just need to think about strong base, strong acid. What should the start point be? What should the end point be? It gives us C. Which diagram shows the correct electronic configuration of a nitrogen atom in the ground state? Now, it has a lot of words here to confuse you. It's just the electronic configuration of nitrogen. So if you think about nitrogen, you're going to have this, okay? You'll have your fully filled 1s and 2s. So this is saying 1s, 2s. They'll be fully filled. So we know that this one is wrong. It's either of these. And then we know that in the sp, it's sp3 nitrogen. So the configuration would be A. Why is that? Why is sp3 filled like that? Well, this one also technically has 3 electrons in the p, but we should know that electrons, they fill the empty orbitals first, and then they start pairing up to avoid repulsion. So yeah, that's the only one that works. Again, refer to your periodic table. It's an easy question. Alright, so it says, which row shows a gas that would deviate the least from ideal gas behavior? Okay, before we even look at it, let's identify what ideal gas is. So an ideal gas is a gas in which the particles, the gas particles, are in constant random motion. Okay, that's the first key thing. The second key thing is that in the container that the gas is filling, we can say that for an ideal gas, the volume that the gas takes up is negligible, right? It's so small we can count it as negligible. Now, the third parameter is that an ideal gas, the particles of this gas should not exert forces on one another, thus influencing the motion, right? We should say that the particles should not actually exert the forces on one another. Now, unfortunately, ideal gases are ideal. We have real gases in reality that deviate from this ideal behavior. And these real gases deviate more under certain conditions. Now, these conditions, firstly, is high pressure. Now, if you think about why it does this, if you think about having a container such as this, it's a very small container, and you have of gas particles here, right? It's really full of gas particles, completely full, and it's a really high pressure, right? You have this high pressure. All of a sudden, the volume that these gas particles take up in this really small container, because it's at high pressure, yeah, it's no longer negligible. There's so much gas in such a small volume that it's no longer negligible, so therefore that breaks ideal gas behavior. The second one is at low temperatures, and the reason for this is because at low temperatures, the molecules are moving slower, so there's less kinetic energy to overcome the attraction between the individual particles. So if you think about what we said about the gas particles exerting forces on one another, this starts occurring, which breaks ideal gas behavior. So low temperature and high pressure. So we know that these two would deviate from ideal gas, but we want to see the ones that deviate the least. So it's one of these two, between phosphine and ammonia. Okay, now this is where most students get stuck, because I'm sure you're taught about these ones, but this is more about thinking. See, if you think about ideal gases, another thing that would break them is strong intermolecular forces, right? The behavior of ideal gases are hindered by strong intermolecular forces because of the same logic that we said, that the actual particles should not be influencing the motion of each other. They should not be exerting forces on each other, right? But when we have strong intermolecular forces, this unfortunately occurs. So between phosphine and ammonia, which do you think would have stronger intermolecular forces? Well, for phosphine, we know that phosphine is polar, but it has a weaker intermolecular force compared to ammonia, which has hydrogen bonding, which we know is the strongest intermolecular force. So we know that in terms of these two, phosphine would deviate less than ammonia due to its low intermolecular forces, and therefore we go with A as our answer. There we go. Question number 6. Which of the following shows the shape of S and P orbitals? Okay, so S, we know it's a circle. When it's drawn as a circle, it's spherical. So we know that S is going to be a G. P, we should know, is a dumbbell, right? We have P, Py, X, drawn really badly. So yeah, Px, Pz, but that's not Pz. Pz, yeah. But yeah, so It's pretty easy to see S&P. It's D. It's not a hard one. All right, which row shows the correct formula and electron configuration of the species in calcium nitride? So we have the formulas here and electron configuration of the, okay, sure. So first let's identify the formula, right? This should be pretty easy. Well, we know calcium's in group 2, and form of Ca2+. We know nitrogen is in group 15, so it's going to be N3-, okay? There we go. We have our two ions here. So how would we do that? Well, we can just do the drop and swap method. It's not too difficult. We just drop and swap these two, right? So it's going to be Ca3 and 2, right? Basically, I just drop this exponent to here. I'm sure you can understand the logic behind it. It's just trying to balance the charges, but that's a quick way to do it. So Ca3 and 2. Okay, we have that, so that eliminates Ca2 and 3. That gives us a 50-50 chance. That's what I mean. Like, a lot of these questions, they make it really easy, because that was super easy, and I already have a 50-50 chance of getting the multiple choice right, which I can make even easier if I just read the rest of the information. So yeah, just try and make it easier for yourself by doing the easy parts first and then working on the harder stuff. Okay, so we have Ca3N2. Now, as for the electron configuration of the ions, right, we know that the Ca atom would have argon 4s2, right? But we're not doing with the atom. We know that it's an ion, so it's a Ca2 plus ion. We know it's losing 2 electrons, so it's going to be just argon, right? Which gives us this. And we don't even have to look at the last part. We know it's going to be D. But the same logic applies for part D, but we don't for the N species, but we don't have to look at it. We know it's D. There we go. Question number 8. Diagrams of 4 stable allotropes of carbon are shown. Which row correctly identifies each structure? Okay. Without even looking at the rest, just get fullerene out of the way. It has such a unique structure, the buckyball. So let's match up fullerene with Y. Oh, they just gave it to us. I mean, none of the rest have fullerene at Y. Interesting. So yeah, we know it's going to be A. I'm surprised they didn't have multiple fullerene at Y, because it's so distinguishable. But if you wanted to know why the rest is where it is, we should know that graphene is a sheet, right? It's not like graphite. It has the same bonding structure, except it doesn't have this 3-dimensional structure. It's a sheet like in Z. And for graphite, we can see it's basically the sheets layered on top of each other like that. And then for diamond, we have the tetrahedral structure that's so unique to diamond. Yeah. All right, in which of the following molecules do all atoms obey the octet rule? Classic question. You know what? Let's just do each of them. To be honest, I think at this point, if you've done a lot of past papers, this should not even be something you have to solve. You should just know it by heart. I want to tell you the answer to start off with, because you should know that BF3 is an exception to the octet rule, and you'll be able to figure out the other two aren't an exception. But yeah, since BF3 is the only exception, 1 and 3 are the only ones that obey the octet rule. Okay, so now just to show you guys the proof behind it, we have NF3. So nitrogen has 5 valence electrons, okay, and we know it's going to form 3 bonds with fluorine. So 5 valence electrons, 3 bonds, okay? That gives our nitrogen 3 bonding pairs and 1 lone pair. That's 8, okay? 3 bonding pairs, okay? I'm making this a bit confusing, but essentially, it's just not erasing, okay? We have 1 bonding pair, 2 bonding pair, 3 bonding pairs, and 1 lone pair, right? And that gives us an octet, okay? For PCl3, I'm just going to try and explain it in wording so that, because I don't want to draw everything. Okay, 5 valence electrons phosphorus has, and it forms 3 bonds with chlorine. Okay, so there's 2 bonding pairs, and then we have 1 lone pair. And yeah, for chlorine, it has 7 valence electrons. It forms 1 bond. That's 8 valence electrons. So every molecule here is going to obtain the octet. It's going to sustain the octet rule. Okay, so yeah. If you're wondering where the 5 valence electrons are, it's 4, 5. Okay, 1, 2, 3, 4, 5, and then the chlorine would be here, there, and then it would have its own. It would have its own electrons too. Okay, For our BF3, I'm sure you see it everywhere because the IB tries BF3 all the time. It thinks it's going to catch us soon, but we've seen it for years. Like, we've seen BF3 for years. So boron has 3 valence electrons. Okay, that means it forms 3 bonds with with fluorine, and that only gives boron 6 electrons. Right, that's the difference between the rest. If you just look at the other two, nitrogen and phosphorus, they have 5 valence electrons. Boron has 3. So when we have boron and we have these 3 bonds, all of a sudden we don't have any other electrons in boron to complete its octet, and that means that it's an exception to the octet rule because it's electron deficit. It's missing these electrons. There we go. Alright, N2O can be represented by 2 Lewis formulas, and we have the 2 structures there. Which row correctly identifies formal charges and the more stable structure? Okay, so this is formal charge. It's pretty easy. Formula, I believe it's formal charge is the valence electrons minus the lone electrons plus half bonding electrons. Yeah, lone pair electrons, half bonding electrons. We use that logic for structure X, okay, and we use that logic for structure Y. What do we get? Well, 5 minus 2 plus 3 is 0, right? 5 for nitrogen, 2 lone plus 3. So it's 6 bonding electrons divided by 2, which is 3. So 5 minus 5 is 0. So we know it's going to be 0. Okay, it's one of these two. Let's see if these are the same. So this is plus 1 minus 1. So these two are different for this nitrogen and this oxygen. So let's do this oxygen. It saves us time, right? Because they're the same for the rest of these ones. They share the same formal charge, but they differ here. So make our lives a bit easier. So let's do structure O's, this oxygen, right? So this oxygen, 6 minus 4 plus 2, right? So we got 2 from the half of 4, then we got 4 from the lone pairs, and then so that formal charge is 0. So it's A, right? And it also affirms that X is more stable because it has the formal charge over the more electronegative element. 11. Which row puts these molecules in order of decreasing bond angle? So the highest bond angle first, and then the decreasing bond angle next. Bond angles are just memory, but it can be a bit challenging because some of these, actually no, these ones are out pretty easy. Okay, so we have CH4, H2O, C2H4, and NH3. Okay. So CH4, we should know methane has tetrahedral geometry. Bond angles, I won't draw it like that actually. Bond angle, we should know tetrahedral is 109.5. Okay, pretty simple. So we have established CH4 is 109.5, H2O. Yeah, we should know that H2O has this bent structure because of its lone pairs, and that leads us to this 104.5. It's bent, but it's also bent with this tetrahedral electron geometry. So it has tetrahedral electron geometry, meaning that it has 4 electron domains around it, but 2 of those domains are lone pairs, meaning that there is going to be repulsion causing this bond angle of 104.5. Okay, then let's do our ethene, C2H4. Okay, C2H4. We should know that it is sp2 hybridized because it has sp2 hybridization. It falls under trigonal planar geometry. Trigonal planar we should know is 120 degrees. Okay. Finally, we have ammonia. Yeah. So ammonia is NH3. I won't even bother with the hydrogen. Ammonia, we should know that it has a tetrahedral electron geometry, but it has this one lone pair, and this lone pair means that it's called trigonal pyramidal. And trigonal pyramidal, you'll see multiple different numbers online because it does vary depending on the molecule, but roughly all you need to know is it's below 109.5 and it's roughly 107 degrees. Okay, so it's not asking for the actual numbers, it's asking for decreasing bond angles. We know the highest the highest bond angle will be our C2H4, and then our lowest bond angle will be the H2O. And this is the highest, this is the lowest. CH4 is 109.5, which will be the next, and H3 will be is lower than that, which will be the next, and yeah. So yeah, it's going to be C. Okay, the following TLC was obtained from a mixture of naphthalene and naphthol. Polar silica was used as the stationary phase and a non-polar hexane as the mobile phase. Okay, and it gives us naphthalene and naphthol, and then it wants us to say which one is naphthalene and the RF of naphthalene. Wow, I'm not gonna lie, I usually am always saying how quite easy these papers are. This is quite a difficult question. It requires good knowledge. So the first thing you need to account for is that we're using a non-polar hexane as the mobile phase and a polar silica as a stationary phase, right? So when we have a polar silica stationary phase and we have a non-polar mobile phase, that means the less polar compound is going to travel further, right? That's how TLC works, right? Because we have the non-polar mobile phase, the less polar is going to travel further because of this non-polar mobile phase and a polar stationary phase. Okay, now we got that out of the way. Which one of these is less polar than the other? Well, we can see this. They gave us the physical structure, so we can see it. We can see naphthalene just has this structure, and naphthol has a similar structure, but with this hydroxyl group. And of course, this hydroxyl group is going to make it polar. So naphthalene non-polar, and we have naphthol polar. So what does this mean? Well, we know the higher one, the one that moved further towards the solvent front, that's going to be the one that's naphthalene, because a non-polar is going to travel further in these stationary and mobile phase conditions. So we know X is going to be our naphthalene. So now that we identified that, let's just get the number right. RF. Okay, how do we get the RF? Well, we need to get the distance, okay, from here. So we need to get this distance, and we need to divide it by the distance of the solvent front. Okay, so the solvent front seems to be roughly at 6, right? Sorry, I'll write the formula out if I was being confusing. RF is the distance of the spot, right? So spot distance, and we divide it by the solvent front, SF, distance, SFD. Okay, so the solvent front is roughly at 6, and we have our spot, which is at 1, 2, 3, 4, 5, right? 5 over 6. We know what 5 over 6 is, 0.8. There we go. But yeah, I think it's quite difficult. I'm happy the IB is throwing in questions like that, because it's good they're testing your reasoning, but I would say that's quite a difficult question. 13. Okay, Kekul suggested the structure of benzene with alternating and single and double bonds. Famous structure of benzene Kekul proposed, but turns out it was not. It's actually more of a resonance structure, and which piece of evidence disproves this structure? So let's just go through it one by one. Benzene has a formula C6H6. No, that doesn't disprove it. It's still C6H6. Benzene is an unsaturated molecule. No, not relevant. Not relevant. All single bond C have the same length. All the CC bonds have the same length. Let's put a dot there. Benzene can be hydrogenated. No, that's not the evidence. The answer is C. Now the reason why is because Kekul suggested a structure that has these alternating single and double bonds, right? We have this. But we know that the double bonds, they have a higher bond strength but a lower bond length, right? They're shorter bonds. If the structure of alternating bonds was true, then if we look at all the bonds in benzene, then we would have seen that, we have some shorter bonds and we have some longer bonds. But what we do see is that they're all the same length of bonds. And this suggests that we have something that's more of a resonance structure like that, where the electron is being shared, blah, blah, blah. Okay, germanium has several stable oxidation states, which row show these species in order of increasing radius. Well, we should know that cations have the smaller radius, and this is because there's a more positive charge in the cations, which leads to smaller radius because of stronger attraction to the nucleus. Also, in cations, there's often less shells of electrons, if we're going by that. So it's just going to be a smaller atomic radius, ionic radius. Therefore, if we're looking at this, we want to have the largest cations, the most charged cations, having the smallest radius. And then as we go here, we want to have the anions. The anions are larger because the more negative charge, the larger radius, because less attraction to the nucleus, there's more electrons. If we're thinking the ratio of protons to electrons, there's more electrons, so the electrons can move further from the nucleus as they're not as strongly attracted to the nucleus. And yeah, so by that logic, we should know that the furthest to the left, right, if we're doing increasing radius order, is going to be the 4 plus, then 2 plus, then neutral, and then 4 minus. It's going to be a very simple, Which statement explains the trend first ionization energy from sodium to chlorine? Well, sodium to chlorine, we should know that's across the period. We're going this way horizontally. And what do we know about going horizontally? We should know that as you go down the period, the nuclear charge increases. Which elements would react with each other most vigorously? Okay, so it gives us potassium bromine gas, potassium chlorine gas, sodium bromine gas, sodium chlorine gas. Okay, so general principles, we should know that for the alkali metals, the reactivity increases down the group. So we should know that, oh wow, that's an ugly pen. Sorry about that. Potassium has a greater reactivity than sodium. For halogens, on the other hand, it decreases down the group, right? So we should know that chlorine will have a greater reactivity than bromine gas. So by that logic, if we want the largest reaction, we want potassium and chlorine B. There we go.